So first, I mean, from the starting itself, we are just talking about high voltage architecture. Let's understand why the high voltage is required. So I mean, these are the basic equations. As I told before, don't felt like insulted if I'm trying to explain basic things about electrical engineering. There are a lot of mechanical engineers are there. So the power is equal to the voltage into current. It just like for a mechanical engineer, it is torque into speed. So P is the rated power of the system, V is the rated voltage of the system, I is the rated current of the system. So this is about the electric motor basic diagram. The torque of a electric motor is directly proportional to phi1 and phi2. Phi1 is the stator flux density, phi2 is the rotor flux density. So the torque is proportional to phi1 and phi2. And actually, if you take this sort of architecture, phi1, let's assume phi1 is the stator and phi2 is the rotor. Here the rotor is here the rotor is a permanent magnet. That means phi2 is fixed here. The only variable is phi1, and the phi1 is directly proportional to the current of the system. Okay, and the current, if you take this architecture, we are applying V, maybe this is the battery voltage, and there is a back EMF V, which is proportional to the d phi by dt. This is coming from the Maxwell's equations. So the current going into this motor is difference between V is the applied voltage, E is the back EMF, V minus E by R is the resistance of the stator windings. So if the speed of this, I mean, if this is rotating at a higher speed, the back EMF will be more. So I used to pump, I mean, I need to increase more voltage, the terminal voltage, to pump more current into the motor, and the torque is proportional to phi1 and phi2. Phi2 is fixed and phi1 is directly proportional to the current. So if you want higher torques at higher RPMs, there is no other way than going to the high voltages. That's how the high voltage is coming into picture. And the second point is the power is equal to the voltage into current. If I am using a electric passenger vehicle, typically the voltages is between 300 and 500 volts. What is the reason is the motor cost, I mean, it is driven by the economics. For a typical passenger vehicle which require around maybe 100 kilowatt power, I mean, for acceleration, and 30 kilowatt power to cruise at 120 kmph, that will be the cost of the motor is most economical if the voltage is around 200, I mean 300 to 500 volts. In case of a higher buses, I mean, if you're talking about 12 meter or 10 meter buses, the power requirement is huge, and the motor is cheaper if the voltage is around 900 or 800 volts. So this is the main reason why we are going for high voltage. I mean, even you can bring the examples of Ticor EV and Mahindra e Verito, which are operating at 72 volts. But compared to the higher voltage system, they are operating at they are much inefficient. So the most cheaper version of a motor and the most efficient operation will come at 300 to 500 volts for passenger vehicle based on the power requirement, and around 800 volts for a buses, I mean 10 meter 12 meter buses. We can explain this through other scenario. If the I is more, that means if the power is more, if I'm using lower voltage like 72 volts, I need to pump more current into the system. And the resistance of this cable, it depends upon the type of the material I'm using and number of tons I'm using. So the I square R is the power loss. So if the power is more and V is less, I need to pump more current into the vehicle to maintain the same power, which will be inefficient. And the other constraint is, if I am keep on increasing the voltage, cost for the insulation will increase. So there is a break even based on the power. So that's how the passenger vehicles are more or less operating at 300 to 500 volts, and the commercial vehicles like 10 meter buses and 12 meter buses, they are operating at around 1000 volts. The basic philosophy which is governing these voltages is the most economical operation and the most efficient operation. That's how the voltage came into picture. So the basic purpose of this slide is why we need high voltage. I just want to make this to you. If the any voltage more than 60 volts DC, that is a high voltage. If any voltage more than, if the AC voltage is more than 80 volts, that is a high voltage. So 60 volts more than DC is a high voltage, and more than 80 volts in case of AC is a high voltage. So let's go to the high voltage electric powertrain. Just let me bring the differences between LV, low voltage powertrain, and high voltage powertrain. In case of an internal combustion engine, we use 12 volt power supply. I mean, whatever the automobile or two wheeler you are going to talk about in the present scenario, in the 12 volts the positive is connected to the load, and the negative of the battery and negative of the load, it is connected to the chassis. This is done to save the copper. I mean, I will use the chassis as a return path, and the positive will be supplied by the separate copper cable. This is just used to, and if there is any short circuit, that means the short circuit of positive and negative of the 12 volts battery, that is not severe if the voltage is less than 60 volts. But when I am switching from low voltage architecture to the high voltage architecture, I need to isolate the both positive and negative from the chassis, because here if there is a single insulation breakdown, that means if you think this positive is insulated from the chassis, a single point breakdown between positive and chassis will cause the short circuit on this battery. But here, even if there is a base insulation breakdown between either positive and chassis or negative and chassis, that won't cause any short circuit. The short circuit happens only when both positive and chassis and negative in chassis are between positive and negative. Insulation breaks down, then only short circuit happens. And actually, if you see, the power dissipation is P equal to I square R. That means if the currents are more, amount of power dissipated in the short circuit resistance will be more. So the amount of power dissipated in case of high voltage is more. So we are not taking the chance. We don't want a single isolation failure to cause a short circuit. That's why in case of high voltage systems, both positive and negative are isolated from the chassis. Let me go to the second circuit. Actually, this is a question to everybody who is listening to this lecture. Please note down what will be the voltage of V1 and voltage of V2. Here there is a 300 volts. The chassis is actually any metallic part on the automobile, we call it as a chassis. So the 300 volts is connected to the loads. These loads can be anything between electric motor to the, maybe it can be electric motor as shown before in the different types of electric loads in a electric architecture. It can be a electric motor, or it can be a DC-DC converter, or e-compressor, or onboard charger. So if somebody connects a multimeter between positive and chassis, what will be the voltage? If somebody connects the multimeter between negative and chassis, what will be the voltage? Please note down based on your analysis what you will get in these multimeters. And the next thing is, if somebody is standing on the chassis, that means somebody is touching the metallic part of the automobile and then touching the positive of the automobile. This is 300 volt system, which is a high voltage system. I mean, this is a pretty much like XEV. Any electric vehicle is having more or less 300 volt system. So whether he will get shocked or not. Similarly, if somebody is standing, maybe he's touching the chassis, that means any metallic part on the automobile, and touching the negative of the battery pack or DC link, whether he will get shock or not. So what will happen here is 300 volts is connected to the loads. Since this 300 volts is connected to the loads through the cables, the cable is having copper wire. On the copper wire there will be insulation, the rubber insulation. The insulation between 300 volts and chassis, let's call it as a R1. Similarly, the resistance between 300 volts and chassis, call it as a R2. But generally R1 equal to R2, because we are using same sort of cables for positive and negative. So actually, if it is a 300 volt system, what you will get here is V1 equal to 150 volts, which is half of the supplied voltage. Similarly, here also V2 you will get as a half of the supply voltage. But still, if somebody is trying to touch the positive of the battery pack, who is touching the chassis of the automobile, he will get any shock, because the current flowing through this particular person who is touching the positive is equal to 300 volts divided by the resistance of the person plus the resistance of the negative to the chassis, because he is coming in parallel between the negative to the chassis resistance, which will be very high. It will be in mega ohm. So the current flowing through this particular person is in micro ohms. Similarly, here also the current flowing through the person is micro ohms. That's why we use isolated grounded systems. We used to call it as a isolated grounded system. The main difference is, in case of a 12 volts architecture or low voltage architecture or conventional engine architecture, that the negative point of the battery, it is connected to the chassis. They used to do this to save some amount of copper here. But in case of high voltage electric vehicle, especially electric vehicle, both positive and negative, they are isolated from the chassis, so that a single point of short circuit with the chassis, it won't create any issue to the automobile. To create a short circuit, there should be two failures between positive to the chassis and negative to the chassis. Even if somebody is touching the negative and standing on the chassis and positive and standing on the chassis, it won't cause any issue. But to make this happen, first of all, we need to measure the insulation. Let me tell you what is the insulation. This is about the insulation monitoring system. This is the integral part of the high voltage XCV powertrain. For mechanical engineers, I try to bring it back. I mean, I try to simplify it to the KVL and KCL laws. Okay, so let me see. The basic purpose of insulation monitoring is if any insulation lost between positive and chassis or negative and chassis, since both positive and negative are isolated from the chassis, that will be detected at the initial loss itself, and it won't get propagated into short circuit of both positive and negative. That is the basic purpose of insulation monitoring. Let me see how this will happen. So this is the battery. That means the powertrain V battery. It's more or less around 300 volts in case of a conventional automobile. And R1 is the resistance between positive of the battery and chassis. Similarly, R2 is the resistance between negative and chassis. Actually, I haven't shown this. This is connected to the chassis here. I haven't shown it here. So similarly, these are the 2.3 mega ohm, 2.3 mega ohm. These are pre-made resistors. 80 mega ohm and 2 mega ohm are the pre-made resistors, but KP and KQ, these are the switches. So in this scenario, KP is closed and KQ is open. If you write the Kirchhoff equations, I will get VP and V down, V up and V down, which are measured here. So these are the straightforward writing of the Kirchhoff current law. V up is actually, this is potential divider rule. V up, that means the voltage across the string is equal to V bat, that means battery voltage, into R1 parallel to 2.3 mega ohm parallel to 80 mega ohm, because this switch is closed, divided by the whole resistance. That means R1 parallel to 2.3 mega ohm parallel to 80 mega ohm plus R2 parallel to 2.3 mega ohm, because this switch is open. This is the voltage I used to get. I mean, V up by V down. Similarly, next what I will do is I will open KP and I will close the KQ. So here I will get one more equation. My basic purpose is finding the R1 and R2, which are the insulation between positive and chassis and negative and chassis. So I am doing different permutations and combination by using these switches, so that I will get two algebraic equations. If I solve these two algebraic equations, I know V battery, I know V up and V down, which I am measuring through the maybe electronic measurement. I want to make two algebraic equations, so I will get R1 and R2. So this is the second variation in scenario 2, where I am opening the KP, I'm closing the KQ. Here also I will get the second equation. So I know V up, V down, I don't know R1 and R2, but I know these all the remaining things. So if I solve these two equations, 1 and 2, I will get R1 and R2. These are the insulation resistors. If there is any short circuit between, I mean, if the R1 is shorted, I will get the value here itself, or R2 is shorted, I will get the value. So if there is any insulation breakdown, then I immediately open the battery contactor. This is the basic safety which will prevent the hazard. This is how the insulation system work in a high voltage automobile, electric automobile. So next thing is actually I'm touching the basics of the topics. I'm not going in depth. I'm trying to touch. First thing is we are using a electric powertrain. For a passenger vehicle, we require higher voltages to operate efficiently, at the same time to reduce the cost of the automobile. So if you're going to higher voltages, you are having certain hazards, like somebody get the shock. That is one thing which will be prevented by this insulation monitoring. That means if the insulation breaks, if the insulation is reduced, I won't even connect the battery. Second thing is, if it's the high voltage, let me explain what will happen here. So all the loads, when I'm saying loads, the loads will consist in electric motors, onboard chargers, or DC-DC converter. They consist of huge amount of capacitance. I mean, in case of a vehicle like Hyundai Kona or Tata Nexon EV, this will be around 1000 microfarads, this capacitor. The current flowing through the capacitor, I equal to C into dV by dt. The current flowing into the capacitor is multiplication of capacitance into rate of change of voltage. This is pretty much a basic 12th class math, physics actually. So If I connect, I mean, let's assume this pre-charge contactor is not there. If I'm directly connecting this voltage source to the loads, then the current will be very high. This will be around, I mean, if the dv by dt, and if I take 1000 microfarads, it will be around 2000 amps to 6000 amps, which will weld this contactor. If there are any fuses in between, that will blow those fuses also. So we need a pre-charge, to reduce this current to the normal values. So the pre-charge will happen like this. I mean, first they will connect the battery to the loads through a pre-charge resistor. So when you are connecting this 300 volts through a pre-charge resistor, the current is controlled once this capacitor is charged. I mean, initially the capacitor act like a short circuit, and after some time, this is the basics of the transients, electrical transients. After some time, the capacitor has an open circuit. This capacitor is charged to 300 volts. Once this capacitor more or less charged to the 300 volts, the pre-charge conductor is opened, main conductor is closed. This is called as a pre-charge. Since we are going to high voltage, we can't connect the battery directly to the loads. We require certain resistance and a certain contactor to charge the DC link voltage to the more or less equal to the battery voltage. So this is one, I mean, the first thing is insulation measurement. Because we are going to high voltage, we need to control the hazards. Second thing is the pre-charge contactor. These are the two things required. Profiles in the xev industry, and the different job profiles are system engineering. There are different job profiles. I'm just skipping the charging system because we have less time. So the job profiles are system engineering. That means if I want to design an automobile just like Hyundai Kona or Nexon EV, what is the size of the motor I require, or what is the size of the battery I need, or DC converter or e-compressor, that is defined by the systems engineering. That means there is a engineer who will get the requirements from the marketing team. That means they want to achieve 0 to 100 kmph in 10 seconds or 5 seconds, or they want to maintain a range of 300 kilometers. So they will get all these requirements. They will convert these requirements into system capacities. Like I want a 30 kilowatt hour battery, or I want a electric motor with 40 kilowatt. That is defined by the system engineer. That means he will use mathematical equations to model the system, and he will get the capacities of the individual component, either onboard charger or DC-DC converter or electric motor or the battery. That is provided by the system engineering. Next is the thermal system design. That means since the, as I told before, both the traction system and battery system require cooling. So what is the coolant power required? What is the compressor side required? What is the RPM of the coolant pumps, which is pumping the fluid throughout the, I mean, coolant fluid throughout this thermal system and battery system? That is defined by the thermal system design engineer. Next is powertrain modeling. Once the system engineer define these parameters, the powertrain modeling engineer will define the mathematical modeling of the individual components, so that if you want to test certain thing, there is no need of an actual vehicle. He can run the simulations in the, we used to call as a high hardware in loop simulation platforms like Opal RT or DSpace. That means he will just solve the mathematical equations. Next thing is application software development. The requirements, let's assume a requirement. If somebody open the door of a bus, the vehicle not supposed to run more than 5 kmph. This is the requirement. So the software engineer, the application software development engineer, he will get the requirement, and he will put a sensor. There is a sensor in the door. If the door is opened, even somebody is flooring the accelerator pedal, he requests the torque from the motor more than which is required for more than 5 kmph. So this is done by the software development, application software development team for the powertrain controller. Next one is the verification and validation. The verification and validation engineer, he will read the requirements and he will create different scenarios, and he will verify whether software developed by the application engineer is working properly or not. Next one is the component testing. The component testing engineer, he will get the individual components. He will test all these components on the bench rather than on the vehicle. I mean, let's say DC-DC converter is supposed to deliver 1.5 kilowatt amount of power. He will just put a load of 1.5 kilowatt on the bench, and he will just test whether it is supplying it or not, whether it is violating any of its limits, like whether it is crossing its temperature or not. So that is the purpose of the component testing engineer. Next, HV component design and development. That means he will design the system with the proper insulation requirement and the current requirement. That means he will define what is the fuse requirement, what is the contactor requirement, what is the connector, high voltage connector requirement. All these things will be done by the HV component design and development engineer. Remaining things, I'm not going into the job profiles.